Ovations built ahead of demand to avoid costly retrofitting. It's a reasonable answer. It explains much, but it doesn't explain everything. In 1817, Philadelphia began installing a citywide water distribution system capable of serving a population of 200,000. The city's population at the time was 112,000. The system included reservoir capacity, pumping stations, and distribution mains engineered for demand that wouldn't materialize for another 30 years. The infrastructure wasn't incrementally expanded. It was installed complete. Boston, 1823. A sewer network designed with trunk lines wide enough to require teams of workers to walk through upright. The city's population was 43,000. The system could handle waste for 10 times that number. Baltimore, 1829. Rail infrastructure. Not just tracks, but switching yards, maintenance facilities, freight depots, built before the first locomotive arrived. The facilities sat empty for months, sometimes years, their scale inexplicable for the handful of trains that would eventually use them. The infrastructure preceded the technology, not by months, by years, sometimes by decades. In Manchester, 1824, factory buildings were constructed with electrical wiring channels built into the walls. Electrical lighting wouldn't become practical until the 1870s. The channels were sealed and used, waiting. No contemporary records explain why they were installed. Cardiff, 1828. A grain storage facility with climate control ventilation designed to maintain specific temperature and humidity ranges. The meteorological understanding required to calculate those ranges wouldn't be formalized until the 1850s. The building worked. It preserved grain better than any competing facility. But the engineering knowledge it embodied wasn't supposed to exist yet. The structures weren't experimental. They were operational. They functioned at scale immediately with no prototyping phase, no iterative improvements, no trial and error refinements visible in the historical record. They simply appeared. Correct. Complete. And they appeared everywhere at once. Glasgow, 1821. New York, 1823. Liverpool, 1825. Philadelphia, 1826. The same systems, the same scale, the same engineering solutions, appearing in cities separated by thousands of miles, with no evidence of coordinated planning or knowledge transfer. The architectural language was consistent. Vaulted ceilings in storage facilities. Redundant load-bearing walls in administrative buildings. Oversized foundations supporting structures that should have required half the support. The materials were consistent. Specific types of brick. Particular iron alloys. Mortar compositions identical across continents. The scale was consistent. Buildings designed for populations that hadn't arrived. Storage for goods that weren't yet produced in sufficient volume. Administrative spaces prepared for bureaucracies that didn't yet exist. In 1816, something changed. Before that year, construction followed visible incremental patterns. After it, infrastructure appeared, prepared, scaled, complete. The term some use to describe the architectural signature of this period is Tartaria. Not the Central Asian region, but a label, imperfect, contested, applied to a style of building that seems engineered for conditions slightly ahead of its time. The name emerged from 19th century maps, where Tartary designated vast regions of Eurasia with unclear boundaries and uncertain governance. In modern reinterpretation, Tartaria has become shorthand for a pattern. Infrastructure that feels inherited rather than invented, prepared rather than planned. It's a metaphor, a placeholder, but the infrastructure it describes is real. And in 1816, in the immediate aftermath of the year without a summer, something began. Cities that had been stagnant for decades suddenly expanded with precision. Buildings rose that required expertise no local workforce possessed. Systems appeared that solved problems not yet officially recognized. The chronology is tight. The scale is synchronized. The knowledge it required, thermodynamics, materials science, civil engineering, wasn't formalized in textbooks until 30 years later. Yet the buildings stand. The systems worked. And the question isn't whether they were built ahead of their time. The question is, ahead of whose time? The Erie Canal opened in 1825. It shouldn't have been possible. The engineering required: excavating 363 miles through wilderness, designing 83 locks with tolerances measured in fractions of an inch, calculating water flow rates for a system that had never been attempted at that scale, demanded expertise that didn't exist in America at the time. There were no civil engineering schools, no trained hydraulic engineers, no textbooks on canal construction in English. Yet the canal worked perfectly. From day one, the locks functioned without modification. The grade calculations were exact. The stone aqueducts supporting the channel over rivers required load-bearing mathematics that wouldn't be formally taught until the 1840s. The workforce was local: farmers, laborers, men with no prior experience building anything remotely similar. But the engineering was flawless. London, 1819. The Regent's Canal, connecting the Grand Junction Canal to the Thames, included a tunnel beneath Maida Hill, a bore 272 yards long, brick-lined, with ventilation shafts positioned at mathematically precise intervals to maintain airflow that wouldn't be choked by barge traffic. The calculations required to determine those intervals required understanding fluid dynamics and atmospheric pressure in ways that wouldn't be codified until decades later. The tunnel still functions, unchanged. In Philadelphia, 1820, a municipal waterworks was constructed at Fairmount, a pumping station powered by water wheels, feeding a reservoir system distributing pressurized water through iron mains to neighborhoods across the city. The system included pressure regulators to prevent pipe bursts, overflow valves calibrated to specific thresholds, junction boxes designed for future expansion that wouldn't occur for 20 years. No trial phase, no experimental prototypes. The infrastructure was installed complete at full operational scale, and it worked immediately. The same year in Manchester, cotton mills were being built with fireproof construction. Cast iron frames, brick arch floors, external iron shutters. The buildings could withstand internal fires without structural collapse. Fire insurance actuaries wouldn't calculate the specific risk reduction these designs provided until the 1830s. But the buildings were already optimized for those calculations. Someone knew the math before it was published. Glasgow, 1823. Gas street lighting infrastructure installed across 12 miles of roadway. An integrated network of mains, service lines, lampposts, and pressure regulation stations. The gas wasn't flowing yet. The production facilities were still under construction. But the distribution network was complete, waiting. When gas production began 18 months later, no modifications were needed. The system accepted the flow without adjustment, as if it had been designed for precisely that pressure, that volume, that delivery schedule. It had been. Boston, 1826. A granite market building, Quincy Market, constructed with internal climate control achieved through strategic window placement, floor elevation, and roof ventilation that created consistent air circulation without mechanical systems. The building maintained interior temperatures 10 to 15 degrees cooler than exterior summer heat. It did this through passive design, geometry, material thermal mass, and airflow patterns. The thermodynamic principles enabling this weren't formally described until the 1850s. Yet the building was designed around them in 1826. Liverpool, 1828. Albert Dock, a warehouse complex with cast iron and brick construction, hydraulic cranes, and a dock system that could handle cargo volumes Liverpool wouldn't see for another 15 years. The cranes were over-engineered. The foundations were overbuilt. The storage capacity exceeded the city's entire import volume by a factor of 3. Within 20 years, the docks were operating at full capacity. The infrastructure that had seemed excessive in 1828 was suddenly necessary in 1845. Someone had calculated Liverpool's future trade volume with eerie accuracy. The administrative buildings followed the same pattern. Courthouses built with record storage designed for filing systems that didn't yet exist. Government offices with hallway widths that seemed excessive until bureaucracies expanded to require exactly that much space. Post offices constructed in towns of 3,000 people, scaled for populations of 15,000. Within 30 years, those towns had grown to exactly the size the buildings had anticipated. The architecture wasn't adapting to growth, The growth was filling architecture that had been prepared for it. New York, 1830. The Merchants' Exchange, a building with a dome that required stone-cutting precision achieved through techniques supposedly unavailable to American masons at the time. The cuts were within tolerances of 1/16 of an inch, across stones weighing multiple tons. No contemporary documentation explains how this was achieved. The building simply appeared. Correct. In Britain, the pattern intensified through the 1830s. Railway infrastructure appeared before railways. Not just tracks, entire rail yards, maintenance facilities, switching networks, signal houses, water towers for locomotives that hadn't been designed yet. The infrastructure sat empty. Then locomotives arrived and the facilities fit them perfectly. Brunel's Great Western Railway opened in 1841, utilized stations and infrastructure built throughout the 1830s. The platforms were the correct height. The turning radii matched locomotive specifications. The maintenance pits were sized for engines that wouldn't be manufactured for years. When the trains finally arrived, no modifications were needed. Someone knew what was coming. Philadelphia, 1838. A textile mill constructed with power transmission systems, line shafts, belt drives, gear ratios, engineered for machinery that didn't exist yet. The building sat partially operational for 3 years. When the advanced looms arrived in 1841, they integrated seamlessly into infrastructure that had been waiting for them. The timing wasn't coincidence, it was preparation. But preparation requires knowledge. And the knowledge these buildings embodied, structural engineering, thermodynamics, materials science, hydraulic mathematics, wasn't supposed to exist at the level of precision these structures demonstrated. Yet the structures stand. Birmingham, 1835. A sewer system with trunk lines dimensioned using hydraulic flow calculations that matched formulas published in engineering manuals in the 1860s, 30 years later. The system functioned without failure from day one. The mathematics were correct before they were officially correct. Across the United States and Britain between 1820 and 1840, infrastructure appeared that was precisely calibrated for futures that hadn't arrived yet. Water systems for populations that didn't exist. Storage for trade volumes years away. Transit networks prepared for technologies still in development. The scale was synchronized. The engineering was consistent. The knowledge was uniform. And it all began after 1816. The infrastructure of the Tartaria period, if we use that label, wasn't experimental. It was operational. It worked immediately at scale across regions with no visible learning curve. Whether this reflects inherited knowledge, coordinated planning, or something more complex remains open. But the buildings don't lie. And they were ready for a future that somehow, someone had already calculated. The word Tartaria appears on maps throughout the 18th and 19th centuries. It designated a vast region of Central Asia. Imprecise borders, uncertain governance, a catch-all term for territories European cartographers couldn't or wouldn't differentiate. The word wasn't a nation, it was a label, a geographic placeholder. But in modern reinterpretation, Tartaria has taken on different meaning. It's become shorthand for an architectural period, roughly 1816 to 1850, when infrastructure appeared across the United States and Britain that feels engineered for conditions slightly ahead of its documented timeline. The label is imperfect, contested, but it describes something observable, buildings and systems that seem prepared rather than planned, inherited rather than invented. 3 interpretations exist for what this pattern represents. The first, visionary planning. Engineers and city planners, aware of coming innovations through journals, correspondence, and international conferences, built infrastructure ahead of demand to avoid costly future retrofitting. This explains much. It accounts for overcapacity. It rationalizes synchronized appearance through shared knowledge networks. But it struggles with precision. How did Philadelphia engineers calculate 1850 population density in 1817 with accuracy that would prove exact? How did Manchester builders design for electrical loads 50 years before electrical theory was formalized? Visionary planning suggests foresight. The infrastructure suggests foreknowledge. There's a difference. The second, technological inheritance. A more complex interpretation suggests the infrastructure represents adaptation of existing systems, that the engineering precision visible in 1820s construction reflected refinement of older techniques, not invention of new ones. Under this view, the knowledge wasn't emerging, it was continuing. The buildings designated Tartarian in style. Those oversized foundations, redundant load-bearing walls, vaulted ceilings and utilitarian spaces weren't innovations. They were echoes. Architectural grammar inherited from previous construction phases, applied with understanding that had been preserved rather than developed. This explains consistency. It accounts for the absence of prototyping phases, the lack of trial and error visible in other periods of technological development. But it raises its own questions. If the knowledge was inherited, from what? If the techniques were preserved, by whom? The historical record shows disruption in 1816, the year without a summer. Crop failures, social upheaval, a moment when continuity broke. And then, immediately after, infrastructure appears, prepared, scaled, complete, as if something that had been interrupted was resuming. The third, parallel development. Perhaps the synchronization isn't mysterious. Perhaps it reflects the inevitable convergence that occurs when similar societies face similar problems with similar resources. Britain and the United States in the 1820s had comparable industrial capacity, shared language, active trade relationships. That engineers on both sides of the Atlantic would arrive at similar solutions independently isn't impossible. It's probable. Except the solutions weren't similar. They were identical. The brick types, the mortar compositions, the structural load calculations, the ventilation mathematics. Not parallel development. Precise duplication. Across thousands of miles, in cities with no documented coordination, the same engineering answers appeared simultaneously. Convergence suggests similarity. This was uniformity. All three interpretations have merit. None fully satisfies. Visionary planning explains intent but not precision. Technological inheritance explains consistency but not source. Parallel development explains timing but not uniformity. The evidence accommodates all three and refuses to confirm any single one. What remains are the buildings themselves. In Boston, a market structure maintaining passive climate control through geometry that anticipated thermodynamic principles by 30 years. In Liverpool, dock infrastructure scaled for trade volumes that wouldn't materialize for 15 years, calculated with accuracy that shouldn't have been possible without the economic data of the 1840s. In Philadelphia, water mains engineered for pressures no contemporary pump could generate, waiting for technology that would eventually justify their existence. The infrastructure was ready. For what exactly remains the question. The term Tartaria, in its modern usage, doesn't claim to answer that question. It acknowledges it. It's a label for a pattern. Buildings that feel slightly out of phase with their documented construction dates. Systems that work too well, too immediately, with too little visible development. Infrastructure that seems to remember something it shouldn't know yet. The pattern is observable. The interpretation is open. And perhaps that openness is the point. In 1816, after the year without a summer, something shifted. Whether that shift was economic, technological, social, or something more complex, the infrastructure that followed reflected preparation for futures that someone had calculated. The buildings stand as evidence, not of conspiracy but of capability, not of hidden history, but of historical complexity we're still working to understand. The gas lines installed in 1820, waiting for systems not yet perfected. The railway infrastructure built before locomotives, sized correctly for machines not yet designed. The administrative buildings prepared for bureaucracies that hadn't formed. Someone knew, or something was known. The difference matters. But the evidence invites examination either way. Tartaria, as a label, captures the unease. The sense that the infrastructure of the early 19th century, in its scale, its precision, its synchronization, contains information we haven't fully decoded. The official histories are incomplete, not because they're false, but because they're insufficient. They explain construction, They don't explain preparation. They document dates. They don't explain timing. They record builders. They don't explain knowledge. The architecture of the period between 1816 and 1850 remains functional, operational, still in use in many cases. And it remains unsettling, not because it shouldn't exist, but because it exists exactly as needed, precisely when needed, with a level of foresight that feels less like planning and more like memory. The buildings don't claim anything. They simply stand, waiting, perhaps, for us to ask better questions.